So next up, starting morphing and shape from biology to engineering.
Hello. So thank you for being here. Thank you, Angela, for the invitation to share some of my interests. Okay, so what I will be talking about is recent things that happened across my two affiliations. One is in a math department where I was doing mathematical mechanobiology, and one is in a robotics department where I was trying, and so it's an attempt of bringing these two things together. So learn from biology to try to build interesting objects. Okay, I decided to do it with iPad. Let's see how it goes. Because my laptop crashes when I do PowerPoint on Zoom. I don't know why. So the idea is that biology works with machines, and so we try and build machines inspired by biology. And usually when I say starting from common ground, this is a very common ground experiment. It's a sperm cell, which is at the origin of most of you. And it's a very simple machine. And so there is a container, a cargo, the head, which contains a payload, which is the genetic information in the form of DNA. And there is a propulsive apparatus, which is a beating tail. And that is what is used for delivery. Okay, very simple. And you can conceptualize simply, and you can try to reproduce it simply with a red blood cell, 5 microns across, which may be functionalized to contain something. Then there is a tail made with magnetic beads. And by applying an oscillating magnetic field, you can have it beat. And by the beating of this thing, you can make it move. Okay, and so this is a successful thing. And the obvious application of this is targeted drug delivery, right? So you can reach a very minuscule site and deliver a drug when it's needed, So very fascinating. Now you look at this and you can go in several ways. If you are technologically oriented, you may ask yourself, well, how can I make it autonomous? Because in order to produce that magnetic field, you need a gigantic electromagnet outside, and the natural construct is instead autonomous. Okay? So you can go in this direction. Another direction, which is much simpler, is to observe the two, and to observe that while the natural one swims with the tail back and with the head in front, which means with the payload in front, the other one swims with the tail in front. The main difference between the two is that the first one will arrive at the target in the right orientation for delivery. The other one needs a maneuver. And so you can start asking the question, how do I control the maneuver? Is there a way in which I can turn it around? Or does it have a reverse gear? So is it forced to swim with the tail in front, or can you do something to the body architecture or to the way to control it to give it a reverse gear? And this is a question of controllability. Okay, so there's a huge field which is control theory, in which you have the tools to answer these questions. And in fact, related to the topics of the workshop, this is reminiscent of Apollo missions and the LEM module, should it land with the head, with the feet. And this was, and also reaching the moon, in fact, was one of the prime and first applications of Kalman filters. And so lots of things that are relevant maybe to this community. So there's a whole, avenue you can go there, but I will not go. So I've been working a little bit in this area, but I will not talk about this today, which has to do with mathematical swimming. Swimming as a control problem. which is a complicated problem. It's a fluid structure interaction problem, and it's an infinite dimensional control problem, because really swimming is about engineering a flow field, so an infinite dimensional solution of the Navier-Stokes equation around you, so that you acquire a certain trajectory. Okay, so there's a whole direction in which one may go okay, we can talk about it. Instead, I want to talk about a small thing today, much smaller, which has to do with our own attempts to model certain organisms to learn lessons from them. Sperm cells have been studied very, very intensively. Other unicellular organisms, like this one, have been studied less intensively. In fact, this is studied by, we have a group, an international group that studies these objects. This is called Euglena. This Euglena network consists of maybe 30 people worldwide, so we have a small community. Anyway, so this is Euglena. It's similar to what we saw before, so it's something that can swim in a different way. So instead of beating a posterior flagellum, it beats an anterior flagellum. So it pulls itself in a fluid instead of pushing like a tail. And so this is Euglena swimming. It's already interesting. The control problem for this organism is interesting. And in fact, the trajectory you're seeing are sort of universal. So, I mean, one can even prove theorems saying that if you have an organism that swims by beating periodically a flagellum, a cilium, an array of cilia, and it swims far away from walls, then it will generate a trajectory that's always a general helix. So the trajectory you're seeing there, which is a helix with some perturbations, is somehow the result of a general theorem. So all organisms will display that behavior. But then the interesting thing about this organism is that if you tamper with its natural behavior a little bit, so for example, you put it into a tapered capillary, so you now start exploring the effect of confinement. So you have it swim in a confined environment, and you engineer the confinement so that it's bigger and bigger and bigger. So it's more and more confined. And you can study quantitatively this effect of confinement through the radius of the capillary that is shrinking. Then this organism exhibits a change of behavior. So it starts by swimming. Now it's swimming. But then when the tapering, when the radius of the capillary becomes bigger, it starts changing behavior. It doesn't really know what to do. Basically, you're interfering, this is our interpretation, with the free motion of flagellum. So it starts feeling the presence of a wall, right, while swimming. And then something happens and it changes completely the behavior. And now here you're seeing that instead of a swimmer, this is a crawler. Okay, so confinement has transformed this organism from a swimmer to an earthworm, like a crawler that exploits frictional interaction with it. Okay. And so, I mean, this is pretty interesting. I mean, this is a gait change, like a horse that instead of walking may trot or gallop, which is a very well-studied problem about optimal use of energy resources, so to speak. Here, the interesting thing about this is that this transition happens in a unicellular organism, so an organism with no brain. Okay, so everything here is it's all hardware, there's no software. So here we have seen somehow sensing of confinement, response, and decision-making, all in a hardware architecture without a controller, which is very interesting if you are interested in questions of miniaturizing, objects. So you want to build very small things that are not like the Boston Dynamics Atlas, which is very big and there's a lot of controllers. Here, everything is passive. Okay, so it's hard wired into the system, and this makes it possible to have like a 50 micron object. Okay, so this is our toy, and so we've worked a lot about this, but today I will talk a little bit about just one little aspect, which is the last one. So how is it possible that this guy is able to execute these shape changes? Okay, so the beating of the flagellum is a very interesting topic. Maybe we'll go back to this towards the end of the talk because it will resonate with other similar motions of elongated objects, for example, in plants. But most of what I'm going to say next, maybe also to draw some analogies with other systems that are of interest to the organizers of the series, I want to talk about how does this organism execute these shape changes. Okay, so it will be about morphing, and this is a closer look at how this organism manages to basically moving inside a tube is, I mean, it can be done if you are able to protrude a bulge on your body and have this bulge moving along your body. So in this way, it's like having hands that push against the wall and make you propel. Okay? So this is the mechanism. Now, this organ doesn't have hands, so the way the protrusion is made is not by a dedicated organ like my hands, my arms, but it's by protruding a bulge in the body. And this is done thanks to this architecture of the envelope, of the cell envelope, which is in a sense a little bit intermediate between bacteria and eukaryotic cells. Bacteria have walls, rigid walls that are solid. Eukaryotic cells have a plasma membrane, which is fluid. And what you see here is an ultrastructure made of protein-made pellicles, so which are solid, however, which can slide next to one another. So it's the sliding is almost like a plastic flow, or you want a fluid motion between solid objects. And so this is intermediate between a totally fluid object and a totally solid object. And so maybe I can show it again. Maybe not. I don't know. What do I do? I do this and I do that. Okay, yes. We can see it again. So the sliding of these pellicles, these strips causes this shape changes at the level of the body. Okay, so what is happening here? What is happening here is that deformations of the surface cause Gaussian curvature. The bulge is a surface with two curvatures, Gaussian curvature, and so this is what is happening. Control of curvature, Gaussian curvature, thanks to deformations of the surface. So what we are going to do is to use the Gauss theorema egregio, okay, to understand this. And it will happen in a few slides. Yes?
What is the source of the activity here?
What is?
The source of the activity.
Yeah, so I don't know whether I have slides about that, but underneath these strips, so if I have two strips,
yes,
there are microtubules,
okay,
and there are molecular motors running on these microtubules, and the running on the microtubules causes relative sliding.
okay. So it's the motors, kinesin or whatever motors are. It's the motors that are.
Yes. I'm not sure whether it's kinesin or dyneins, but it's molecular motors of and actually, yeah, okay. Yeah. So, I mean, I can tell you more maybe later. Right. So this is the pellicle in a little more detail. So this is with the scanning electron microscopy. And here you see a clear correlation between geometry and texture and optical and arrangement of the strips. Where the strips are almost vertical, the thing is skinny and long. When there is a big angle, the thing is fat and short. Okay? So this is the first mechanism to understand. How is it that sliding can cause this changes of, the next one, there's a slide answering your question. So how does this basic correlation between, say, radius of a cylinder and orientation of the strips on the periphery? Okay, so we will.
So what happens if it's not a cylinder? What happens if it's flatter in one direction and wide in another? Will it try to swim or stay floating?
Actually, this is obtained by flattening. Because what you're seeing here is squash between two and between the slide and the cover slip of the microscope. So this is is it clear what I'm saying? So
Yeah.
So in this configuration, it's doing what you're seeing.
I don't know what they have.
It's not going laterally in this configuration. But if you don't squash it, it may do that sometimes. I mean, this is not the natural behavior.
Yeah.
So the natural behavior is swimming.
Yeah.
So it's like a rigid cigar. Then when you in some situations with crowding, for example, when there's a lot of them, it can start doing this motion, and it may be a bit more complicated than what I've shown after now. Several of them doing something, yeah. And yeah, I mean, yeah, maybe I can show you other things. Okay, and so here is your question. So what is causing this? If you take a cross section and you look sideways, you will see the ridges and the troughs and valleys, which produce the optical constants when you see them away. So the strips are roughly 500 nanometers wide, so half a micron. This scale bar, the scale bar you see in the bottom is 500 nanometers. And if you look very carefully in the region where they overlap, there should be some circles. Okay, so I cannot point it online, but I can put it there. So these are the sections of the micro. It's not very well, I mean, it's not very clear maybe from the screen, but there they are. And so there is where the molecular motors act and cause the sliding. And so the mechanism is something like that. Okay, so the mechanism that we are seeing is this sliding induced by molecular motors acting on microtubules underneath the strips, and this is the thing that should cause the shape change. Okay, now how do we understand this in a bit more quantitative detail? Okay, I mean, Gauss theorem egregium, maybe this is. And if one wanted to write a formula for the Gaussian curvature in terms of Christoffel symbols, it would be something like that. But you will see much more friendly versions of this formula, because this is very difficult to understand anything there, like from there, except that the theorem says that the Gaussian curvature can be computed from the first fundamental form and derivatives of this coefficient. So the metric, the changes of distances and angle tells you everything about the Gaussian curvature. And one important thing is that I typically use this slide to say something about the Gauss theorem egregium, but maybe one important thing is besides the pizza eater version of the map maker problem, I will not talk about it. I mean, it's popular to popularize this. The thing I wanted to emphasize is the fact that it's important that so there's two ways of looking at the metric tensor. One is differential geometry, metric tensor. I measure lengths and angles, and another one is mechanics. So what you're looking at is the F transpose F. So you take the deformation gradient, you take the transpose times that, and you build a matrix that tells you how angles and lengths change, right? But the important thing is that in order to get Gaussian curvature out of a cylinder, you need that the stretches be modulated. They cannot be constant, they must change. And so I typically use this object, which if you push on it, you produce my famous bulge. So Gaussian curvature, because it's curved not only in this direction, but also in this direction. But for that, you need to modulate the stretches along this direction, right? So here, at the ends of this object, this has been cut with a thermal object that has fused the ends. So here, changes of radius are forbidden, while in the center, they're not forbidden, right? And it's a change of radius along this axis that produces the Gaussian curvature. So let's remember this, that we have to modulate the stretches along tangent plane, if you want, or along the surface. Okay. Right. So the basic mechanism, what I will show is two things. One is the basic mechanism of changing radius by sliding. And the second mechanism will be modulating this change of radius to produce the Gaussian curve. So the first is, I can decompose the metric change into the composition of several operations. And I will use a piece of paper just to illustrate that. So I will do composition of elementary steps, each of which does not change the metric. And only one step will change the metric. And so this will be a way of computing the way the metric changes because of the sliding of the strips. So the first operation is to unfold the cylinder isometrically, as you would do with a piece of paper, which is unstretchable, right? So this object essentially deforms isometrically. So there's no stretches and change the angle in the plane. And so the first operation is to make it flat, make a cylinder flat with an isometry. The second step is to operate the sliding. Now, if you have a flat thing and the strips slide, now I will do a uniform sliding, both along the vertical direction and along the horizontal direction. The vertical direction is okay. The horizontal direction is actually, remember, is what used to be a parallel, right? So whenever I say horizontal, I mean parallel-wise, and whenever I say vertical, I mean along the axis of the cylinder, the original cylinder. And right, so, and in all what I will say, the horizontal things in the horizontal direction will be constant, because I want to do things that are not modulated in the direction of the parallels, because I'm going to do axis symmetric deformation. Okay, so you will always see things that are trivial along the horizontal direction. Maybe later they will be modulated along the vertical direction. First slide, there's no modulation neither in the vertical nor the horizontal, so the sliding is constant. Okay, now you do the sliding, so you shear the rectangle, and the tangent to the angle that you see there, gamma, is the ratio between the vertical displacement and the horizontal displacement. And you use Pythagoras theorem to see that by shearing, the W that used to be horizontal has become the hypotenuse of a triangle. It has become longer, right? And the amount by which it has become longer depends on the angle by which you shear. The more you shear, the longer it is. And the ratio is square root of 1 plus gamma squared. I mean, this is the thing that we can compute using Pythagoras theorem. Okay, so this is the only change of metric. Now I rotate, and this does not change the metric. Then I fold back, again isometrically, and this does not change the metric. Except that when I fold back, the red things do not generate vertical lines, but they generate helices. Okay? And so the sliding, so this is the basic mechanism by which you change the radius of the parallels and you shorten the meridians. Right? So by changing the straight thing into a helix, you've made it shorter and fatter. So
Why did you not do directly that?
say that again.
Why did you not shear it directly like this?
Why did I not shear? I'm not understanding.
Oh, okay, because you needed to rotate to.
No, I did unfold, shear, rotate to make it horizontal, fold back to make it a helix.
Yeah.
So that's the typical, when you straighten a helix to compute the equation, you typically do that. Anyway, so this is the basic mechanism that transforms a cylinder into a cylinder. So if you have a cylinder of sliding strips, you can make it another, you can generate another cylinder, which is shorter and spans a larger radius with a uniform sliding of the strips. Okay. Okay, now that we have learned this, now we have to modulate along the vertical direction to produce a bulge. So the idea is that there will be certain regions where you do a little shear here, you do a little shear and you produce a little radius change. And then there are regions where you do a large shear and you produce a large radius change. And so that's the bulge. Okay. And now the question is, you can do two pieces of cylinder. Now the technical question is how you join them. And okay, trust me, you can. You can join them either in the brutal way I've done here with cones, or you can do it with more sophisticated ways that are smooth. But the good thing about this construction is that now you can, it's a construction that you can move along the body, and this will produce a bulge that moves along the body. And so this is the basic mechanism that Euglena uses to push against the lateral walls of the cylinder and to move along. Okay, all this can be done in a much more sophisticated way by really using the Gauss theorem. The good thing about this is that if you do axisymmetric metrics, so you never, all your deformations are independent of the coordinate along the parallel. And so everything is independent of u in this notation. And it only depends on v, the vertical coordinate. Then the form, okay, this is the metric that we have. You know, the gamma is the shear, and it only depends on v. And when you plug the vertical coordinate, so I'm doing, again, I say it again, an axisymmetric shear. So gamma is independent of u. It only depends on the vertical coordinate v. Okay? Now, when you plug this into the formula for the Gauss theorem, instead of getting the formula that we saw before, you get something that is much, much more readable, which is this formula here. And this formula is starting to become, okay, if you stare at it for long enough, it becomes super clear. But okay, the first thing you see is that there's a comma v. Comma v means derivative with respect to v. And the minute you do something that does not depend on v, gamma, the inner gamma, becomes zero, and so zero Gaussian curvature. And actually, this is the case. You need a little bit extra to say that you have a cylinder. Okay, so this is the way of producing cylinders. Gamma comma v equals zero. And then you see that there is a more sophisticated way of producing zero kappa by not having gamma constant, but having gamma times gamma comma v constant. Okay, so you can have a non-constant gamma that produces zero Gaussian curvature, and this is the cones. Okay, so if you solve this, you get the cone. And then you can solve this equation, I want a sphere. Okay, so let's say, is it possible with this mechanism to produce a sphere, so with constant positive Gaussian curvature? And the answer is yes. So you solve this as a differential equation, gamma comma v equals constant, you solve it, and you find the pattern by which you have to actuate your Euglena so that it produces sphere. Okay, and sphere is not the only solution. You can produce many, you can produce, these are the solutions for constant Gaussian curvature, positive or negative. So you get all this family of shapes, and from which you, for example, you can somehow use to do any transition region you want between the small cylinder and the fat cylinder that we have over there. Okay, so the good thing about this is that by using the identity in both ways, by running the identity from left to right or from right to left, you are solving two problems, which in the literature now they are called the direct and the inverse morphing problem. The direct morphing problem is if you give me the gamma, so if you tell me how you are actuating, compute the surface, the shape you get. Okay, you can do. The inverse one is design a shape, design a Gaussian curvature, and find the actuation mechanisms that you need to implement. And this is the other way. And okay, so this is very satisfactory. Right. And this is okay. And so this is where the analysis takes you. And now let me say where engineering comes into play. Okay, so we have, in a sense, understood the mechanism by which Euglena moves and stuff like that. And then it turns out that there is no engineering device, to my knowledge, that uses this as a shape changing mechanism. Okay, so And so we are testing this statement now with a patent. So we've patented this mechanism for. The important thing about this mechanism is that in engineering language is the following. I mean, there are many mechanisms by which you can change the shape of something by. So, okay, maybe I should say we are using the Gaussian theorem egregium as a morphing algorithm. Okay, so, and it's not my idea. I will quote the person that inspired this approach, meaning that you are imagine that you can actuate a surface with a metric that changes in the way you want, then this will produce a surface with a certain geometry, right? So this is not, this is, okay, I mean, Gauss was thinking about everything, but in this way, we are using the theorem as an actuation engine algorithm, right? A morphing algorithm. Right, and there are many, okay? So here, I'm producing this by pushing, but if I were actuating the lattice of the fibers that composes this object, okay? So if you look at it close by, it's basically a meshwork in which certain fibers are like this, certain fibers are like that. They don't slide very much at the intersections, and basically each cell deforms like this when you compress and like that when you extend, right? So this is the basic mechanism. Okay? So this is called a pantograph. And, it's the thing on trains in countries where there is electric trains. And, okay, so this does exactly the same thing that we were doing in a sense. What is the basic difference? Well, this mechanism has a limited stroke. Okay? So once you have compressed like that, that's it. Once you have extended like that, that's it. So there is a maximum stroke that this morphing mechanism can exploit. Okay. Sliding is unlimited. You can slide as much as you want. So the advantage of this mechanism is that the stroke is limited not by the microscopic actuation mechanism, but simply by the size of the strips. So this mechanism stops working when one strip has slid the whole length of the other one, and then the thing disassembles. If you have strips of infinite length, you can achieve infinite shape change. For example, you can change this cylinder, the vertical cylinder, into this annular disk, and if the strips are infinitely long, you can reach a disk that is infinitely long. Okay. Right, and so this is now the game that we are playing, and at the engineering level, so we 3D print these guys and we experiment with them, etc. Okay, now I want to move towards some other things. So this concept is very, very general and is not due to me. So actually, maybe I should have shown the other slide first, but so I was using sliding as the basic actuation mechanism, and but I've been describing another one that uses stretching, which is this. Okay? So instead of having strips that slide, I can have surfaces that stretch along the. So this mechanism is something that is contracting along the parallels and the meridians, and it's expanding along the parallels, right? Okay, and actually this is the way this stream has originated through, so problems of morphing through growth in plants, where the stretching is really a proxy for having more stuff. Okay, so imagine that you're building a cylinder by laying bricks, and then at some point of a fixed size, and then at some point you start putting more bricks. Okay? So this mechanism will produce something which wants to be with larger and larger radius, so it will produce something like that. Okay, and okay, and so this was the actually the context that generated all this. So here you see examples, but let me go directly to any things that you can do. But okay, this is really the slide that should have been there before. So the first column is what I was describing, and it was used to somehow explain this mechanism of morphing by growth, and in particular this oscillations that happen when you're too greedy and you try to enforce gradients of this stretch, if you want, that are too big, and you encounter problems that you understand through differential geometry about the non-embeddability of a metric if certain conditions are violated. And so what you're seeing there is the fact that the axisymmetric metric is not embeddable, and these oscillations that violate axisymmetry are produced from this mechanism. And maybe in the center you see an artistic version of this concept in which instead of growth it's working with crochet, in which you add more and more units, so to speak. And then maybe one before the last, you see a version of this in which the deformations are due to the swelling of a hydrogel, or in the bottom, deformation due to pneumatic inflation by inflating something, and you make it bigger. And so I want to say something about this this pneumatic actuation because it's very, very popular in robotics. So let me show you this concept. Okay. This concept in pneumatic actuation. So what you see in the circle that you see there is the structure without air. Then you pump air in it. The tubes inflate, so they go from the flat state that you see on top to the inflated state. They're made of a material that is essentially inextensible. So when they inflate, they basically have to go out of plane, and so they span a smaller area, and so they induce a contraction in the direction perpendicular of the tube. Is it vaguely understandable? So if you have, this object and you inflate it, the span is smaller. Okay? So this is what we are seeing. So by having a family of parallel tubes and inflating them and neglecting the out of plane dimension, you think of it on the 2D projection, so as if it was zero thickness, basically you have a metric that causes no changes of length along the tubes and a contraction perpendicular to the tube. This is a uniaxial deformation field with a clear symmetry, the symmetry of the tube. And it's very closely reminiscent of what happens with one less dimension in, for example, materials with an internal director, like liquid crystal elastomers, for example. So the change of shape of liquid crystal elastomer is often due to the fact that there is a director field. And when the material orders in the nematic state, something happens. When the material disorders in the isotropic state, the opposite thing happens. And typically, this is when you heat up something. Typically, this is a disordering that causes a contraction along the direction of the director. But anyway, it's a uniaxial deformation field. So these two things are sort of related. Okay, right. So let me talk a little bit about the mattress. So this is it's summer in Southern Europe, so people experiment with that on a daily basis by floating on these devices on a mattress. I know. It was a joke. And right. And so, yes. And so the question is, can you make a sphere? Before we were playing with the sphere, can you make a sphere out of an inflatable mattress? And the answer is yes. You have to modulate the metric in the way Gauss has taught you. Okay. And what you see here is a large sphere. So this is meant to illustrate the fact that these concepts are very robust across scales. I mean, they go from the millimeter scale of samples of liquid crystal elastomers to the meter scale of this object. You can think of building, okay, intermediate, you can make inflatable salad bowls. And at this scale, you can make, you can protect yourself from sun, and you make an inflatable igloo. And so what you see here is it's a second version, the second generation of this concept, in which we're using these zigzags. Okay, so let me explain this. So modulation of the important thing is to modulate, and maybe it's easier to describe it with the second generation than with the first. So when you inflate this guy, parallels and meridians, essentially you want that the parallels and the meridians change in a very specific way, and the change of radius has to be just right to produce the constant curvature. But you see that it's very easy to think of this shaping in terms of parallels and meridians. And but if you do that, you must have a biaxial deformation, because the meridian has to shorten of a certain amount, and the parallel has to shorten of a certain amount, and the ratio between the two is given by the geometry. Okay, and so if you have a uniaxial deformation, in which deformation field, in which, for example, only one, I mean, you can only deform in a certain way along in a uniaxial way, you cannot reach a biaxial deformation. Okay. One could think of this in terms of intrinsic property as a rank 1 tensor or a rank 2 tensor. I mean, we need a rank 2 tensor because we need a biaxial deformation. Or we have to do something very, 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 very strange. And the very strange is to find this complicated pattern of the director field that you see over there. So spiraling it around. And it turns out that if you take that construction and you make it, okay, I don't see it. Basically, what you see here is mixing that construction at a small scale with its symmetric. Okay, maybe I can say it later. What I'm trying to say is that the angles here are the same as the angle there. And the angle here is the same as that one, but they've been symmetrized in a way that produces a zig and a zag with the right properties, Okay, so what we are doing here, in a sense, is separating scales. So we need, I mean, Gauss tells us that we need to modulate the metric in a certain way to produce the Gaussian curvature. And what we are doing here is to introduce an intermediate length scale to decouple the material length scale that gives you the contraction from the gradients that Gauss wants, right, at the scale of the structure. And so by doing zigzags, very, very fine zigzags, you can generate a biaxial metric from a uniaxial metric, basically. And then you can use the biaxial metric and modulate it a la Gauss to produce the construction. Okay? So the basic difference between the two constructions is that while on the left, so the one on the right is more symmetric, right? So the principal direction of the metrics are on the parallels and the meridians. And the consequence of that is that if you take a point, if you follow the way a point deforms in this deformation, you will see that it does not have displacements along the parallel, so twists, if you will. While the one on the left achieves the same thing, but with a twist, okay? So not a big, yes?
So can I specify, you want a rank 2 matrix? And you're running the linear combination of
No. I take it back. The story. I mean, I think I went too far in that thing, because you can achieve the same thing with a rank 1 matrix. So forget that remark. Okay. So, but the only difference, the real difference, is that somehow there is more flexibility. I mean, the one on the right. So if you allow yourself to modulate at a small scale, and then you take the average of that construction as an allowed metric to use, you have enlarged the palette of metrics that you can use. maybe this would have been a better way of describing it. Okay, so I'm sorry if I misled. Okay, so and maybe to illustrate this, we can do this in a plot. Okay, so the thing I was trying to describe is the thing on the left, where there's several systems. You can apply this to several systems. And the one, so imagine that you do this for liquid crystal elastomers, I don't know, where once you know the strain in one direction, volume conservation forces the strains in the plane perpendicular to yourself, right? So if you put one of these axes, lambda parallel, say the stretch in the direction of the vector, the other coordinate is forced on you by volume conservation. And so you have 1 point. So one material is 1 point on that plot. If you allow yourself to zigzag, you can reach all the things that exchange the two directions somehow. So, if you do this, lambda parallel is what was lambda perpendicular before, right? And so you have symmetrized the plot. You attribute to lambda perpendicular what it was lambda parallel. And then you can find the whole curve joining those two by the intermediate angle. So basically, this construction tells you that if you're allowed to mix at that finer scale, and then you use Gauss theorem with the averages, you expand the palette from 1 point to an arc in that. Okay.
But your intermediate, this will join these two.
Yeah.
That join. Will you have the same concentration there?
Will I have?
Yeah.
Where the 6 and the left come together.
Yeah.
Will you have strain concentrations or either?
Yes. So if you think in terms of patches, imagine, so what I'm saying is that you can build a sphere out of patches. And then when you join the patches, you will get a mismatch however, the mismatch, I'm importing another body of literature into this, and I will tell you where this comes from, but the mismatch will become smaller and smaller as the fineness of the pattern becomes smaller. Okay, so microstructures and blah blah, twinning and this kind of thing.
But you can do it with axisymmetric solution.
Here, yes. Here we were doing, these are all axisymmetric.
Yeah.
I cannot do it always with axisymmetric. I'm not sure I understand where you are. I understand your question, but I don't understand where you want to. So here it was done with axisymmetric, but there are cases in which axisymmetric does not work. Okay, right, and so this had to do with morphing and blah blah, and maybe last topic, so to speak. So plants, we were seeing when we saw plants a little bit, so deformation by growth. So this is one of the mechanisms for deformation. Another one is, so I want to talk a little bit more about plants. And so this is a beautiful, it's not me, again, it's Eran Sharon. I forgot to mention the name. So this is one of the ways plants move. Not plants, certain, so pine cones work like this. So when a pine cone dries up, it opens up, and it disperses seeds. Okay, and this is another mechanism for seed dispersal, and so this is a famous thing. But I find this movie so beautiful. So you're seeing there what he called an erodium perpetuum mobile. So the mechanism is driven by humidity. Okay, so it's a hygroscopic bilayer actually. And so when it wets, it straightens up. When it dries, it coils. And the basic principle that you see here is the bilayer principle, in the sense that when you have two materials that contract, so the most famous application of this is a bimetal strip that is used as a thermostat. So if you have two different metals and that expand differentially, then they will curve upon heating. Okay? And so you're seeing the same thing here, something that is curving upon drying of one of the two. So there is one of the two layers in a bilayer that becomes wet, and it dries up, and it induces this movement. So this is one of the ways plants move. I skipped another way, that is motion induced by growth, and Alain has worked a lot about that, but I wanted to talk more about more passive ways in which plants move. And so this is one way, this is with hygroscopic. And I wanted to show you instead this. So this is another, because it's real engineering, so to speak. Okay, so I want to tell you something about a project in which, okay, there is this idea of doing robotic things inspired by plants, and now this focus here is not to use, to use passive. Okay, it's always to use passive things, humidity, and the concept you use here is what we want to do is to disperse environmental sensors as if they were seeds. Okay, so you have think of them as robotic leaves. Okay, so a leaf falls down, falls on the ground, and then it becomes a sensor for temperature, for whatever happens to it. I mean, you can monitor the color, and you can actually the change of color of the leaves before falling is due to temperature, to the fact that temperature goes down. Okay, so the idea is to disperse biodegradable environmental sensors with drones in remote areas. Okay, and so again, it's exactly a swimming problem, but instead of having a motor, you have gravity. Okay, so this is the fluid structure interaction problem of a free falling object subject to gravity surrounded by a fluid. Okay, and I want to show you, a few things coming together. So the first thing I want to show you is you will see a movie of a shape memory polymer that is put into hot water that causes a shape transition to another shape. Okay, so it starts straight and it will become that object there, and it falls in a tube. So now it's falling, now it's changing shape, and it changes completely the way it moves. And so this motion, this oscillatory motion, is called flutter. Okay, and then I'll show you another seed. Okay, this seed is doing another motion, and this is called autorotation. So you're seeing the late stages of the fall of the seed from when it's 50 centimeters to, it was released at 2 meters. The first meter it falls like a stone, like that, and then it acquires this motion and it moves like that. Changes completely the. Okay, so what is the thing here? Well, so this is motivated by plants, because plants are sessile, contrary to a drone, they do not move around. Okay, so plants have developed this strategy of dispersing seeds, in which often the way of seeding outside of the feet, so to reach large lateral distances, is exploiting lateral winds. And so the slower you fall, the further away you go. Okay, so this mode of fall is conducive to that. Okay? Another one is the dandelion, the parachute seeds that use another principle, but again, okay, so this is one of the things. Of course, if you have a drone, you can decide not to do that. You can go here and seed here, seed there, and exploit vertical fall. Okay? But if you have to fly at a distance and you have to, send lots of seeds, it's important to have this mode also available, right? So the problem here, the scientific problem, is to compute. To actually not compute, to design the best strategy of seeding for these artificial objects. Okay? And the movies are here because this problem is devilish, of course. It's a very nonlinear problem. What you're seeing here are the attractors of the dynamics of a very complex nonlinear system governed by the equation of motion. So there you saw also elasticity or shape changes. And you saw a transition between two completely different ways of moving. Now freeze those degree of freedom. And for example, you get this rigid seed on the right, and that is a rigid object falling. So you still have the equation of motion of rigid body dynamics that are very nonlinear, coupled with Navier-Stokes equation that are very nonlinear. And what we're seeing here is, okay, so what happens here? What happens here is that the basis is the vertical steady fall. This is the basis. Okay, you saw that it was not falling. I mean, at some point it started oscillating, right? Maybe it's because it got distorted a little bit, the bilayer principle, out of standing in my pocket. So this is the basic solution. Okay, so the vertical steady fall. But this solution becomes unstable when you change the parameters of the system. So in particular, one thing that makes the system very unstable, you see it here, if you change the Reynolds number. So this is a rationalization of what is happening in terms of a geometric parameter that keeps, I mean, I star is the inertia of rotational inertia of the system. So the resistance to rotate laterally. And on the vertical axis, there's a Reynolds number. So what you see here is that the Reynolds numbers goes up, which is the speed of fall. Then the steady vertical trajectory becomes unstable. So unstable to something else, okay? And the thing you see here are three attractors of the dynamics. So they are, you know, in the deep nonlinear regime, you know, in large perturbations with respect to this one, which are fluttering, the one you saw before, the one you saw in the tube of the signal. So this, I don't know whether we can get this fluttering here. Okay, so actually you saw an initial fluttering, and then you saw a full turn, and that is called tumbling. Okay, so depending on the parameters, you see all these, and there was also a hula hoop here. So this is called hula hoop. This is an auto-rotation mode, which is a bit strange because the coordinates are not scaled the same. So you would see it going very fast, but this is really I mean, it's a tiny deviation from the vertical. Anyway, so this is another very interesting topic, and so we are very busy with this, in particular with the transition between, I forgot to say, this is a thin disk. So it's an axisymmetric object, and this is the simplest shape that behaves with this complexity. So you are seeing non-axisymmetric fall modes that are instabilities of the basic axisymmetric falling mode, which is the steady vertical trajectory. And the connection between the linear stability analysis of the equations of motion and the fully developed thing is, you know, all to come. And okay, this is what we are doing right now. Thank you very much.
Have you had any interest from the defense industry, like spying devices?
Have I?
Would this, I can imagine it being used if you want to parachute the spying device into enemy territory.
Yeah, I mean, so this is a network,
Yeah.
and I'm not the drone person, and so, but you know, obviously it's a sensitive issue. I mean,
What's the story about the?
I said biodegradable environmental sensor, not bombs, but you know, I mean,
So there was I think it was a Chinese team, I can't remember from where, they made a little device like the Rhodium seeds made of cellulose.
yeah,
So 2 sheets of cellulose shaped the right way with a payload so that it can, and it also self-degradable.
yeah,
It looked like.
very simple. I know. There are a number of groups. I mean, there are several groups that are doing similar.
And they release it with the drone.
Yeah, I know of at least 3 or 4 more groups. One of them is Chinese. Maybe it's the same, maybe not.
I hate to have some
Yeah.
Chinese, it's like.
Yeah.
okay.
But
It's my brain that doesn't work.
yeah, I mean, obviously, you know, there may be different priorities, right? So our priority is science. So we are concerned with this instability analysis. So we've done the stability analysis and attempts to connect the unstable modes with the question of connecting the unstable modes with the attractors of the dynamics. I've not seen, there is a French group that works precisely along this line, and okay, this is not the most popular research line that in this area, but yeah, it's a fashionable problem. There's also a John Rogers, I don't know whether you know him, from Northwestern. He's working on this with these 150 army of 150 postdocs, and
As soon as you get into the working area, there are always big labs. It's fine.
yes,
Your problem about something that you know like this, elucidation, pattern elucidation. Can you attack this problem? You attack by perturbation?
So the way we do it is, in a sense, by averaging, right? So it's a little bit like asking yourself, it's very, I mean, we come from this microstructure business in which you have gradients of something that converge weakly, so they converge in average, but not pointwise. And then the question is whether the things you generate, I mean, so the question is really whether a given limit matrix can be achieved with a sequence of constructions like that. Say.
And the answer is yes. I mean, the demonstration was not super convincing in terms of making a sphere.
No.
It looks
no.
more
Yeah,
like
yeah.
a piecewise
Sure.
approximation of
In
a
fact,
sphere that-
because in fact it was very, very coarse.
But I mean,
So
on the
the
theory
side-
on the theory side, you can actually show
Yes,
that you can
yeah.
prove
For the
by
sphere, yes, yeah.
sequence.
But you have to go fine. So
Yeah.
basically, the thing was built with four layers, and so this was like a curved rank 1 laminate made of 4 pieces.
Pieces of different.
And if you want to get closer to the profile, you have to do a better job.
And then you get hands with them.